Hello everyone, this is PCB, your trusted PCB partner. Today our topic is 4-layer PCB EMI EMC optimization, as well as the secrets and optimization methods of decoupling capacitors. Welcome back to the 4-layer PCB EMI EMC optimization course. In the previous video, we took an in-depth look at the importance of signal return paths for EMI EMC. Today we will focus on another equally critical detail, decoupling capacitors. It plays an indispensable role in suppressing electrical noise and improving system stability. We will learn how to place it correctly, and by combining the concept of return paths, achieve even better PCB designs. The return path, as we mentioned in the previous video, refers to the fact that for a signal with respect to the power supply, a positive signal travels forward, passes through the device, and then returns to the power ground through the device's ground. This forms a return path. Alright, so what are the functions of decoupling capacitors? The first function is to meet the instantaneous current demands of the IC. High-speed digital ICs, such as CPUs, PGAs, VRs, etc., when operating, especially when circuits are rapidly switching, can draw very large currents from the power supply in an instant. The second function is to control power supply impedance. Even if a 4-layer board has a power plane, the power network still has a certain amount of impedance. When the ISA draws a large current instantaneously, if the power supply's response speed is not fast enough, it can cause a sudden voltage drop at the ISA's power pins, or even generates power supply noise, which can affect the normal operation of the IC. Alright, so a decoupling capacitor acts like a small energy reservoir. It stores charge and can quickly release this charge when the ISA needs an instantaneous current, thereby meeting the ISA's electronic demands locally. This is basically the fundamental function of a capacitor. We call it a capacitor because it stores energy. It can both store and release energy, providing support for these instantaneous charges. This effectively reduces the impedance present in the power network, suppresses power supply noise at the ISA pin of the power grid, and at the same time it also isolates noise generated by the ISA, preventing it from spreading across the board through the power network. Let's take this diagram as an example. Here you can see its network VDD and 0V ref. This is a 0.95V power network. Correspondingly, here is the 0.95V power pin of this chip. The capacitor is placed very close to it, serving as a decoupling capacitor. When the 0.95V pin needs an instantaneous current, the capacitor can release the energy stored within it, providing 10,000 or even 16,000 small voltage bursts. Similarly, if noise is generated on the 0.95V voltage, this noise can also be absorbed by the capacitor, preventing it from feeding back into the main power circuit. This is its primary function. Alright, where is the optimal placement for a decoupling capacitor? Where should it be positioned for best result? The placement of the decoupling capacitor is crucial to its effectiveness. The core principle is that the decoupling capacitor must be placed as close as possible to the IC's power pin. The reason is that every PCB component has parasitic inductance and resistance. If the decoupling capacitor is too far from the IC, these parasitic parameters increase, making it impossible for the capacitor to supply instantaneous current to the IC in time, thus losing its decoupling effect. We can simply imagine that electricity is like water, and when the IC uses electricity, it's like it needs to drink water. So the decoupling capacitor is like a cup of water or a reservoir, not a distant water tower. If the cup can quickly solve the problem, there's no need to transport water from a faraway water tower. And when you need it urgently, it might be too late to fetch water from the tower, so it needs to be placed very close. It must be placed right next to the power pin of the IC. One pad of the capacitor should be directly connected to the power pin of the IC, and the other pad should be connected to the ground plane through the nearest VR. As for this beautiful decoupling capacitor, as the decoupling capacitor for this pin, it doesn't need to be very large. It is directly connected at the most fundamental position. Then, on the other end, you just need to place a wire at the closest possible distance to connect it to the ground plane. All right, the number of vias should be minimized. The path from the capacitor pad to the IC pin and the via to the ground plane should be as short and thick as possible to reduce parasitic resistance. So if we can avoid adding vias, we should use as few as possible and also keep the distance as short as possible. For example, on the positive side, you basically don't need to add a via, you can connect it directly. Then, for connecting to ground, since the ground reference plane is in the inner layer, adding a via is necessary, so you should place it as close as possible. Also, when using multiple capacitors together, it's usually necessary to combine several decoupling capacitors of different values to cover the varying noise density requirements from low to high frequency. For example, you would use a large capacity 10 mmF capacitor for a certain frequency range, a smaller 1 mmF capacitor for the high frequency noise area, and a very small capacitor with a fixed value of 0 mmF for specific needs. This depends on the specific situation. Most of the time, we generally use a 1.1 mmF capacitor. However, if the IC is special or has a higher power consumption, we might consider paralleling it with another 1 mmF or even a 10 mmF capacitor. If possible, it's best to place the decoupling capacitor on the same plane as the IC and as close as possible to its power supply pin. The placement of these capacitors follows this principle, keeping them on the same plane as much as possible. This way, the power lines don't need to be routed through vias, which reduces the number of vias, and the capacitors can be placed as close as possible. We can also use a 3-lens camera to take a look and see that all these capacitors are placed on this plane. These decoupling capacitors are all positioned on the same plane and are arranged very close to the power supply pin. Only by combining the return path with the decoupling capacitors can we achieve the best EMI and EMC performance for the capacitor. When the IC draws current from the decoupling capacitor, this current will flow from the positive terminal of the capacitor to the IC and then return from the IC's pin to the negative terminal of the capacitor. If the negative terminal of the decoupling capacitor is grounded and can be connected to a solid ground plane through the nearest via, it not only provides a low impedance power supply, but also ensures that the IC has the shortest and most direct return path back to the ground plane, thus avoiding disruption. Then, as we look at the following content, things will become much clearer. Its D refers to this large horizontal row in the middle. So, following this path, when it needs current, we draw current from this capacitor, absorb its charge, then pass through the D of the IC, and then return through the TNT circuit to this via we just mentioned, back to the capacitor, forming this minimal return path. Uh, on a 4-layer board, a complete ground plane is not only the ideal return path for signal lines, but also serves as a shared heat dissipation area for components like decoupling capacitors and IC connectors. Maintaining the integrity of this plane is the cornerstone of all EMI and EMC optimization. Just like here, it routes out a few necessary lines at this spot, but otherwise preserves the integrity of the ground plane as much as possible. Today, we learned about the key role of decoupling capacitors in low-frequency power supply noise, grasped the principles for optimal placement relative to IC power pins, and also emphasized the synergy between decoupling capacitors and a complete return path. Understanding and applying these EMI and EMC optimization techniques will greatly improve your PCB handling quality and product reliability. I hope that through the content of these 2 lessons, you will be better equipped to tackle the EMI and EMC design challenges of 4-layer PCBs. If you enjoyed this video, please subscribe to my channel for more content. Thank you all.